Hey there, everybody in YouTube land. You probably remember this from a previous video. I have finally decided that I want to get this project finished. And this project has been an ongoing project for, I don't know, about a year now. It's been extremely low priority because this is more of a for fun thing than anything else. And the previous videos I've done on this project, I didn't get a whole lot of interest in it. So I don't know if just people aren't, this is not what people are into or what, I don't know. But anyways, I've got most of the parts in to finish this job. I've finally got all these ordered. I got everything I need to put this board together. I actually bought enough parts to build 2 of these boards because I have another plan, and once I build this one to drive this, whoa, that's a good way to kill the tubes. I've bought another crate, or not a crate, I bought another tray of these indicator displays, these fluorescent indicator panels. I bought another tray of these mainly in case someone else is interested. I could build, right now I only had plans to build just this one, but maybe I'll separate it between left and right channels just for fun, or maybe not, and I've got enough of these boards to build another one. So, but I didn't have enough tubes. Well, I ordered another set of tubes from a contact that I had established back in 2012, and he's not on eBay or anything like that, so you won't find him. So if you need these tubes, let me know. I can put you in touch, or I can sell the tubes to you themselves, because they are overseas. They are surplus stock in Russia somewhere. I don't know, which is kind of strange and ironic because these are not Russian tubes. Anyways, so I'm going to start assembling. I ordered the parts to populate these jacks here, and I have these chips, which actually, the chips for those are right here. And unfortunately, I remember doing in the previous video mentioning you could get these chips at Jamico, and at the time you could. I only ordered about a third of the stock they had because they were still kind of expensive, and I wanted to leave enough there for everyone else. Well, turns out I lollygagged around, and a parts broker bought the entire remaining supply. So instead of other people getting them for their clock projects or whatever they're doing that would genuinely need these driver chips, fluorescent indicator driver chips, which are almost all of them are obsolete except for one, which is the Maxim 6921 series. Instead of, because these are breadboard friendly because they're through hole, and instead of people getting them, because I didn't want to be a glutton and buy them all out, but at the same time, if I didn't get them, there was always a small chance that a parts broker would end up with them, and guess what? The parts broker end up with the other 2/3 of the supply. So, which I'm sure it will show up on eBay sometimes. Right now I can't find them, but I'm sure eventually they'll show up on eBay, and they will be 3 or 4 times the cost of what you could have got them for. So it sucks, but it is what it is. If I'd have known that was going to happen, I'd have bought them all out myself and then offered them up for sale for pretty close to the same price for other people to have a chance of getting them. But whatever, first come, first serve. Welcome to market shares and marketplaces. No dirt off my shoulder, I guess. So anyway, this board, I can't remember if I discussed it in the last video because it's been several months ago, but this board is basically a very simple design, and there's a 3-amp fuse that sits here. There are 2 1,000 microfarad capacitors. Some people say microfarad. Well, I don't say it like that. And then a transient voltage suppressor that if the input grossly overexceeds, this sucker will clamp and pop the fuse. Supposed to, anyway. This is the buffer driver, which buffers the signal coming across the cables that attach all these together. And this is exactly that. This is the array driver. All this guy is designed to do is there's a serial connection between these two chips, and this guy receives all 32 channels of spectrum data, or 32 bands of spectrum data coming from this chip, because this chip, fast Fourier transform, discrete Fourier transform, takes so much overhead, there's not enough room for anything else. And I don't mean processor room as in flash memory room, I mean as in execution time. So there's not much left. So what I do is I calculate all the spectrum data and just blast it out as an array, as a byte array with a beginning tag and an end tag, and that's it. So this chip is designed to receive that and drive the displays, which it'd have plenty of overhead for. So dot mode, bar mode, peak hold mode, all that stuff would be done inside that processor. And down here is the 5-volt regulator and the active rail splitter, which takes the 5 volts, splits it in half, and gives you plus minus 2.5 volts for the ADC to work, because this is an LM324 op amp that's designed with two separate high pass, low pass, a split active filter, because of this chip is not very powerful. So you have a circuit for the high side of the bands and a circuit for the low side of the bands. Otherwise, you would have to overclock the analog to digital converter to get the job done, and it just wasn't happening. So, anyways, that's what that circuit does. And this is a preamp, which is adjusted by this guy right here. And that's it pretty much. And this calibrates the two. So what I would do is I'd do a sine sweep and make sure that all bar levels are level, and these two are adjusted to support that. So anyways, that's that circuit there, and this is the rail splitter to keep that active. Then there's a PWM output, which you can follow. It goes over here. That is a H-bridge driver IC, which what I'm using for that is, since this is a DC circuit, the problem is these tubes, you can just about see this thin wire inside the tube, and it's got a white coating on it, and that's the cathode material. That is actually the emissive material, just like a CRT or a regular old triode tube, or standard vacuum tubes, and that's exactly what this is. This is a triode tube. You have your cathode. You can just see the grid, which is that honeycomb-like material in there, and then the anode, which is the actual gray substrate. I'm not sure what chemical that is, but that whole plate is the anode, and the printed phosphor is what actually glows. But so anyway, this tube uses an AC filament. If you try to power this tube with DC, as explained in this video and several others like it on the web, or the cloud, or whatever the hell they call that these days. Stupid marketing people, I hate them. Anyway, you can't put a DC bias across the filament because that causes a brightness gradation as the resistance of the filament increases on one side from the other. So you have to drive the filament with AC. Well, that's a lot of tubes. So that's going to pull a lot of current, considering each tube is roughly about 150 to 180 milliamps on the filament side. I don't know, that might be a little high. It's more like 120 or so times that many tubes. So the way I'm going to do that is I've got all the filaments attached in parallel, and it gets driven by this chip here, which is nothing more than a simple H-bridge. And the bottom end of the H-bridge is tied together and comes through this resistor to ground. And this is the bias resistor. So in my case, I've got 3 resistors here. This is one side of the filament going out to the filament. This is the other side of the filament going out as the return. So these are switching electrically back and forth. This gets driven high, this one gets pulled to ground through that resistor. And then it'll reverse. This one gets pulled to ground through this resistor, and this one gets driven high. Well, it gets driven high off of this jack here, which could be 9 volts, 12 volts. Well, these filaments are only about 3.2 volts. So the way this is going to work is I'll have resistors in here, and this needs to be as close to ground as possible or the VFD won't get very bright. So chances are I will have this grounded, and I will probably use capacitors here to reduce the amount of voltage flow, or big enough resistors to knock the voltage down to 3.2 volts roughly, 3.4 volts. But the only problem with that is the amount of heat that those resistors are going to throw off. So I have to play with it, because I can't run this off 5 volts, because if I did that, this regulator won't work. It's not a 0 dropout regulator, it's a low dropout regulator. So this has to be 7 volts or better, 6.5 or better for this board to operate properly. So I could probably put 7.5 volts here and get lucky and do that. But the only problem is I still need an anode voltage. Now, how to determine anode voltage? One would be look at the data sheet, which I don't have. Or two, this tube is a statically driven tube. It is not multiplexed. And an easy way to tell that is you could see the grid is continuously connected together. So if it's continuously connected together, you can safely assume that this is a static drive display. And another way to confirm that is if you look in the back and note all the pins coming out of the board, you can see that the anode connections, they're all separate. They're all independent to one another. They're not paralleled. Most vacuum fluorescent displays of the bar graph variety, the top line all has individual connections like this, but they're parallel jump to the bottom one. So they're actually, the two rows are tied together, and then what separates them is separate grids. That would be a multiplex display. This one is clearly a static drive because they all have their own separate connections that move down into the pin array. And that's it. And then once you see that, and then you actually see the display tube and know that the entire tube is one single grid, you can pretty much safely assume that it is a static drive display. So let me get on with it. A static drive display needs a lot lower voltage to maintain the same brightness. Because on a multiplex display, let's say if you've got 10 grids going across, well, that brightness, that's 1 in 10 duty cycle. So that means the current or the voltage needs to be 10 times of what it should be to maintain the same brightness, plus minus losses and some other factors and stuff like that. So if you want, say, 400 nits of brightness, I don't know what this tube is, but just arbitrarily 400 nits of brightness, and there's 10 grids. Well, you got to get 400 nits of brightness, let's say to get 400 nits of brightness, you need 12 volts. To get 400 nits of brightness. Well, there's 10 grids, you need to take that 12 times 10. That's about 120 volts to get the same 400 nits of brightness, which 120 volts seems excessive. So most displays are not multiplexed that high, but most displays you can be okay with 60 volts, 50 volts. And that's what most of them run at. I've seen them as high as 80 volts, and I've seen them as low as 20 volts, 24 volts. It just depends on how much brightness you want to display out of that tube. In this case, it's static drive, 12 volts. Ideally, you want to run these around 15 to 18 static, and it's all right. But I think 12 volts will work just fine. So I have to power this board with 12 volts. So that means this chip is going to see 12 volts. I should have designed it differently, but I wanted to make this thing as simple as possible. I could have made a dedicated 5-volt regulator for this, but this regulator is only good for 1 amp, so I think all these tubes together are going to pull slightly more than 1 amp. Well, let's see if that's 150, 3, that's 6, that's 9, that's 12, that's 1.35, that's almost 1400 amps. So, or 1400 milliamps, so that's 1.4 amps, 14 amps. Wow, where did I get that math? Anyways, that's going to be bigger than 1 amp. This chip is going to get hotter than a firecracker, and it will shut down. So it's easier to come off of this power supply link here and then use these dropping resistors or capacitors or what have you. Or the next thing I can do is I can put a Zener diode right here. You know, like say if this is 12 volts, I can put a 8.2 volt Zener diode, which would give me about 4 volts across the filament. But the problem is it lifts at 8.2 volts above ground. So that means in order for the filaments to be 12 volts, I'd have to have 12 plus 8.2 to get these to maintain the same brightness. So that's the downfall. But I think with some resistor, I can jump this guy to ground and avoid using a resistor on ground. Because since I'm not multiplexing the tube, that's another thing. If you're multiplexing the tube, you're switching off grids at a time. The grids have to be pulled into the cutoff region. So what you do is you use a Zener diode here, and you bias the cathode above ground, slightly above ground, like, you know, 2 volts, 3 volts, whatever, above ground. So instead of 12 volts, you run 15 volts because you're now 3 volts above ground. And then when you're multiplexing, when the filament gets turned off, it gets grounded. Well, that means the grid would be negative in respect to the cathode. So you're biasing the cathode above ground, just like vacuum tube, preamp, and amplifier designs where you've got the cathode resistor coming off of the cathode of the tube. So you'd have the cathode resistor, and that cathode resistor does the very same thing as the same thing here. This is the cathode resistor for all these tubes. But I don't need to bias the tube because they're static drives. So I will jump that out and just put the appropriate resistors in here to knock the voltage down. So anyway, that's it for the filament drive, and I got my programming headers and all that fun stuff. So that's it. That's really all there is to it. So now, without further ado, I'm going to get to assembly. So thank you for watching on the part 2 of this video. Well, I got about that far, and that's as far as I got because this piece of shit here broke down on me. It was only a matter of time. Nice Heiko clone finally died. And basically the way what's happening is you turn it on, it warms the iron up all the way, and then eventually this red light quits coming on and the iron doesn't get hot anymore. And eventually you'll see that light come on a little bit and go off, come on a little bit, go off, and the iron just doesn't get hot. It just stays lukewarm. Now if I turn the power on, let it warm up, as soon as this light goes out, put the power back on, it'll do that. See that? Well, eventually it'll stay on. If I keep doing that, the iron will heat all the way up. But if I stop doing that, the iron cools down again. So, yeah, I don't know what's going on. The original, this is a new wand too, because the one that was with this one eventually went bad. I used it so much the plastic fell apart because the, you know, excellent Chinese quality and all. But so I went ahead and you know, bought a new wand and hardly ever used it, and that's where it sits. So I think I'm going to throw it in the garbage and get a genuine Heiko, and we'll try this again. Alright, we're back at this thing again. Finally got me a new soldering iron and threw that one piece of shit in the garbage. Chinese crap. Anyway, so got all my parts out ready to assemble this thing, and this is as far as I got before the soldering iron crapped out. However, before we go any further, let's just talk about the design a little bit here. This is the 5-volt regulator. This thing is designed for about a 9 to 12 volt input. Actually, it has to be about 12 volts on the input section because the anode voltage comes directly off of that. So this is the 5-volt regulator that drives the 2 microcontrollers. The circuit right here is the active rail splitter. This creates the positive and negative 2.5 volts for the op-amp circuit, and actually that may not be right. No, that's right. VCC2, this is the floating ground. It's 2.5 volts above ground, because this circuit here floats at VCC2 divided by 2, which is this guy here. So we have the RCA jacks, we have the gain adjustment, and a simple unity gain buffer with a 10k ohm input impedance. You know, so we don't overload the source input. And then there's our high and low filter adjustments. And this is our filter network for the spectrum analyzer section. And this is actually a circuit that was found on the internet that I incorporated into the design. So that's the splitter for this. So this thing actually sits at 2.5 volts when it's 0. The 2.5 volts is the 0. So this microcontroller here does the discrete Fourier transform calculations for the spectrum analyzer itself, and that takes almost 100% of CPU time to do that. So what I end up doing is taking that waveform and sending it as a packet to this chip here. This chip here is what drives the display, and this just receives the 32 channels of spectrum data, and it parses it into a bar graph. It does the 10 log conversion inside this chip, and then does the display bar generation, which goes through these buffers here out to the display array, as well as this circuit here. This is a L298 motor control, direction control IC, and the way this has worked is the timer is got 2 sections, A and B, OC1A, OC1B, output compare, timer 1A, output compare, timer 1B, and those sections go into the circuit here, which forms an H bridge. So timer B is going to be the inverter, output B is going to be the inverse of output A. And the way that works, when the timer A and B are switching back and forth, the bottom one's going to be 180 out from the top one, which is going to cause this thing to reverse in a square wave style fashion. So it'll go forward, reverse, forward, reverse, forward, reverse, and that generates the AC signal for the filaments and all the tubes, so we don't have a brightness issue. As well, this line here goes to PC0. This line here turns off the IC, so when I go into standby, it kills the juice going to all the filaments. But this circuit is hooked up to the 12 volt supply, and if I remember correctly, it's hooked up to 12 volts, but the filament only needs about 4.5 to operate. So that's why I have these 2 resistors here, which actually might become a resistor capacitor network instead, to drop the current flowing through the filaments. Ideally, you would want this powered by the same VCC as you want the filament to be fed at. So let's say if the filament needs 4.5 volts plus the drop inside the chip, you'd want to run that chip at 5 volts. But you know, we're dealing with a few amps of current here, which this little guy is not going to handle. So maybe my version 2 design, I will fix that. But until then, I also have another resistor here, which allows the bottom side transistors to float from ground. And what this is for is to actually lift the ground potential of the filaments, so there's no ghosting. And actually, since these are static drive filaments or static drive tubes, I don't need that resistor. I can bypass it. But let's say if this were to power a multiplex tube, a tube that's being scanned, you would have to have this, otherwise it would ghost. And actually, this would probably be replaced with a Zener diode. That way, anything above, it allows it to float so many volts above ground. That way, when the fluorescent display driver pulls the anodes to ground and grids to ground, it actually is below the potential of the filament, so it can't ghost. So then we'll have these guys here adjusted to match the output power. So we have a 12 volt input, and we have a 4.5 volt output. So these guys are going to these things are going to produce a lot of heat. So that's why the footprint on these boards are so big. But to reduce the heat, I think I'm going to put capacitors in here instead of the resistors. I don't know. I'll have to play around with it and see where I go. I think that's why I put a VS jumper in here, in case the 12 volts is too harsh. I can have a secondary power supply feed this chip by itself, so I can jumper it off. But I'm trying to think where the 12 volts comes from. I'm not 100% certain. So there's the feed to the chip. Oh, maybe not. I didn't put a jumper in there. My bad. But there is a fuse. Yeah, so... Oh, I know what the jumper's for. The jumper is for taking the 12 volts to the anode. In case I put a different style of tube in there that won't run off 12 volts, I have to have a secondary power supply. But I should have done the same thing here, which is not hard. I can cut the trace and have a secondary power input for this guy if these resistors get too hot. But we'll determine that at that time. For now, let's get this board assembled. Thank you for watching. Now that we have this thing built, it's fully assembled now, except for these resistors, which I have to calculate later. And, of course, the firmware still needs done, but still in hardware building stage. Got this guy put all together a while back, so now I got to take it apart and start soldering, you know, all the parts on this guy and get this thing together. And hopefully we'll have a working retro spectrum analyzer. That only took hours. Went ahead and got all the driver boards assembled. Nothing special. Just a couple of driver chips, some bypass caps, filter caps, and plugs. And I royally screwed up. When I put the footprint on this board, pin 1 is over here. Well, if you put those connectors in the way I wanted them to go in, pin 1 is now over here. So that means when I make these ribbon cables, when they come back to this board here, I'm going to have to plug or crimp them backwards. So when I plug them in, the pinouts actually match up. Yeah, that sucks. But it is what it is. Not a whole lot I can do about it. So in the meantime, without further ado, let's finish this bad boy up, get it together, and then start working on the programming side of things.